Alright, so we're gonna get the class started today. Let's see, a few things. I think some people are reporting that they have problems installing and getting code blocks to work. So what I'll do first is to kind of just illustrate, how to do that. Not sure, I could not reproduce the problem, so I can only show you, what works for me or what I can tell, is a working combination. So what I'll do is something kind of weird. So I'm gonna start up another virtual machine, running Windows, so I can show you what it looks like when I install it in Windows. And this is also getting recorded because it's Linux running Windows as a virtual machine.
That's interesting.
And it runs actually fairly, efficiently. I don't have any complaints about running it this way.
Was it quicker than the natural one?
Probably cannot be faster, but it's surprisingly, how fast it is. It's just surprising how fast. I would expect it to run a bit slower than this, but it's not too bad. You can see it starts faster than this box running Windows natively, having to log in remotely. So the first thing I'll do is I'm going to uninstall it first. So I'm going to go to code blocks and uninstall it first. So there you go. And then I'll go to the website and kind of show you, which one you should install, because there are 3 options for the binaries. One option only includes code blocks but not the compiler, and then the other 2 would include the compiler. One includes the stable version of the compiler, and then the other one includes the more up-to-date version of the compiler. Either one will work in this class. I don't think we are, in this class it's not picky about which one we use. All right, so we'll just look for code blocks, and then we go to downloads. And then when it gets to downloads, you have to download the binary, not the source code. So not this one here. You have to go to download the binary release. And once you click that link, you will be given a few choices based on the operating system. So go to Windows 2000 XP Vista 7.8, and now you have 3 choices. The first one does not include the compiler, so don't use that. The second and the third choice include the compiler, and it kind of explains here. The code blocks 13.12 main w setup.exe includes the GCC compiler and GDB, and then the other one includes the more up-to-date version. So you can use either this link or this link here to get the file.
The first one doesn't work.
Yeah, the first one doesn't work.
Yeah.
It doesn't work? Okay, so go for the second one, which is a source forge method. And they just make you wait like a few seconds, and you get the executable, just save it and then install it later. The portable version is in beta stage, so that one may or may not work. The virtual machine will work, regardless of the platform, but it's kind of slow, and it does not make use of a hardware acceleration. That's why it's a little bit slow. But looks like this will take. It's getting a little bit faster. 2 minutes still. Okay. So what I'll do is I'm going to hide this window and go back to today's topic. Still logged in because of the morning session. So we go to cisp360. I just want to point out that I added some more stuff to the website. So when you go to basic syntax, expressions and operators, I added this section here. It's logical versus bitwise operators, and also there's a test, quote unquote test, under that. The test is not really a quiz because when people talk about quizzes, they usually imply you have to do it within a certain amount of time, only once to get the points. This one is set up so that you can retake it as many times as you want. It will take the highest score that you get out of a unlimited number of attempts. I have not set any due date, so you can wait until the end of the semester to do it. I wouldn't do it, or you can do it as soon as possible. And every time you retake it, I think 4 or 5 out of the 7 questions, will probably give you a different scenario. So that gives you different test cases and different ways to kind of retest your skills as far as bitwise operators are concerned, and also base conversion. So I strongly suggest you guys to, after today's lecture, make sure you understand the concepts and then go do it. You can do it as many times as you want. It will keep the highest score. So even if you get 100% already and you say, okay, I want to just give it a few more tries. Okay, I want some more examples. Do it again. Okay, you cannot hurt your score by redoing it. Okay, it will take the highest score of all the attempts. So I would definitely use it as a resource to practice on the stuff that we are going to talk about today. Okay. Today's main topic is logical versus bitwise operator. We're going to skip debugger and this part here for the time being. We'll get back to that later. But I feel that it is important to talk about this first, logical versus bitwise operator. And partially it has to do with, I really want to explain how things are represented internally, and just in general, what is a number, versus what is a value. So those are the topics that we'll talk about today. That's the focus of today's lecture. So first of all, we'll start with a number. I'm just going to highlight this number here. 267.25 is a number. A number is basically a way to express a value. Okay, so there's a difference between a number and a value. So let me see if I can get a little prop here to kind of show you the difference. Okay, this is a good prop. The length of this eraser is a quantity. Okay, it's a value. Okay, the length is a value. But how do I describe this length here? I can talk about it in inches. I can talk about it in centimeters or millimeters or whatever unit I choose to use. But it's still the same value. Okay. In other words, I'm just using different ways to express the same value. Is that part okay? Okay. So if that is okay, then we can talk about bases, or base 10 numbers versus base 2 numbers. This is a base 10 number, so typically when we write base 10 numbers, we don't need to use a suffix of 10 to indicate this is a base 10 number. It is usually understood that by default numbers are expressed in base 10. Okay? As a base 10 number, what is 267 and 20.25? Well, you can spell it out, right? Even elementary school students can spell out 267.25 into its components. I break it up to 267.2 and 0.05. Okay, that doesn't seem like hardly this is college material. But when you look at it as a pattern, I can now rewrite that as basically how many of each power of 10 do we have in this number. Still not very complicated, still pretty simple stuff. Once you understand what is a power of 10, it's pretty easy to go from the previous step to this step. Are there any questions at this point about what we have talked about so far? But there is one pattern that you might want to kind of remember, because that's important. Why do you think I choose 10 here, 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 and so on? Because it's base 10, okay? Because it is a decimal number, it is a base 10 number. So I'm choosing 10 as a base, from which I calculate the powers. So if that is a 10, why is there a 2 here, a 1 here, and so on? How does this 2 relate to this number over here?
How many times do you move the decimal over?
How many zeros, right? How many zeros is to the right-hand side of that particular digit? So when we have 2 digits to the right-hand side of 2, then it is representing how many 10 to the power of 2s it has. Is that okay? That's just something that we are so used to, sometimes, we just look at the number and we forget, what each digit is really representing. Each digit of a number is just representing the quantity of that particular power of whatever base that you're using. Okay? It just so happens that we use base 10 by default. It's something that we have learned from childhood and say, well, that's how we represent numbers. Okay. Not very difficult to deal with. So now we transition to base 2. When I use a suffix of 2 after a number, or in parentheses I put a 2 after a number, it means it is a base 2 number. Okay, so sometimes I have to make it explicit because otherwise it can be confusing. Are you talking about 101 in base 10, or are you talking about 101 in base 2? So when we talk about base 2 numbers, sometimes I make it very explicit. What do you think 0 in base 2 represents? What is the value represented by 0 in base 2? It's still 0. All right. That's no big deal. What about 1 in base 2? What quantity or what value do you think it is representing?
0.
It's still representing 1. Okay? 1 is still the same value that it is representing. Okay. What about 1 0 in base 2? Now remember how the base affects the number, and we have 1 0 after on the right hand side of 1. So what value do you think 1 0 is representing?
2.
Is representing 2 in base 10. That has to do with, this is the base, 2 is the base, it is explicit. There's a 1 here, which represents, I have this quantity of 2 to the power of 1, and 2 to the power of 1 because we have 1 0 over here. Is that okay? Is everyone kind of going like, okay, I can see how 1 0 in base 2 represents the value 2, sort of. Okay. And this is the spelled out version of 1 0 in base 2. So all I did here is to say I have 1 of this power of 2, and then I have 0 of this power of 2. Now this part looks kind of confusing because 2 and then a subscript of 10, to me this is in base 10, because 2 does not exist as a base 2 number. Base 2 can only have 0 and 1. So when I use 2, I just want to make it very explicit. This is in base 10, and then the power applies to just 2 itself. Okay, so it looks kind of awkward, but I just want to make it kind of clear that you cannot have 2 as a base 2 number. It is a base 10 number. All right, so now we look at a different number here, which is 1011 in base 2. So the 1 represents that we have 1 of 2 to the power of 3. This 0 means we have 0 of 2 to the power of 2, and I don't even bother to represent it here. This 1 represents that we have 1 of 2 to the power of 1, which is this one here. And then this one here represents that we have 1 of 2 to the power of 0, which is this guy here. So when you add up these numbers, 2 to the power of 3 is 8, 2 to the power of 1 is 2, and then 2 to the power of 0 is 1. And when you add up these 3 numbers, we get 11, which is the base 10 representation of the same value, which is 1011 in base 2. Okay, so which one is it? I mean, is it 1011 in base 2 or is it 11 in base 10? It is both. A number is nothing more than a way to represent a value. It's just like, with me, okay, I can be known as Tak, okay? I can be known as my Chinese name, I can be known as or identified by my employee number, I can be identified by my social security number, my driver's license number, and so on. So they're just different ways of referring to me. It's the same thing here, okay? The quantity of 11 can be represented by 1011 in base 2. It can also be represented by just 1111 in base 10. Are we still doing okay so far with the concept of the base is just changing how we represent a value? Yep.
Can you go over how you got the exponents one more time?
Which one?
Yeah, right there.
Okay, this is 2 to the power of 3 because there are 3 zeros here. And 2 is my base, and that's why I'm using 2 as the base of the power. And then this 1 has 1 0 to its right hand side, and that's why it's 2 to the power of 1. This one here has no zeros to its right hand side, so it's 2 to the power of 0, which is 1.
Okay.
Okay? Okay. So this is kind of like the mathematical way to look at things, but there are other ways to look at it too. Okay? There's an easier way to look at this, especially for people who are still thinking, wow, this base conversion thing, seems kind of complicated. Seems kind of, not so easy to understand. Okay, so here's the question: if I specify this amount, okay, just look at this amount here as a dollar amount. Can you give someone change of this value using the least number of common bills and coins? I mean, I don't think this number will come up as a change at McDonald's, but if it does, do you think you can come up with this change? Yeah. Well, how do you do it? Well, in your mind, first of all, you already have a list of all the common denominations, right? 100 bills, $50 bills, $10 bills, $5 bills, $1 bills, quarters, dimes, nickels. Okay, so you have all of those things already in your mind, and in your mind, you're working with the big numbers first, right? You look at 200 something. Oh, okay, two $100 bills, and then we have 60 something dollars left. Okay, you don't even care 60 whatever, right? $60 something, we'll have a $50 bill. Then we have what, $17 left? Okay, $17, we'll have one $10 bill, and then we have $7 left, $5 bill. Then we have $7 and something left. Okay, 1 5, and then 2 1s, and then the remaining portion is a quarter. So we just give that other person a single quarter. That's how most people work when they look at a number like this, and then they think back. Okay, how do I make that change? How do I make up that amount? And that's more complicated than base conversion. That's way more complicated than base conversion. Okay. So what do we do when we deal with base conversion? One way to look at base conversion is you're changing your money system. So the denominations become not $1, $5, $10, and then 20, 50, 100. You think of it as we have $1 bills, $2 bills, $4 bills, $8 bills, $16 bills, 32, 64, 128, 256, 512, and so on. On the flip side, you can also have half dollars, quarter dollars, eighth dollars, $16, and so on. Okay, so it doesn't work on just the positive side of the power. It also works on the negative side of the power. All right, so let's do this as an exercise. So I'm going to pop up a text editor here. Yes.
Motion.
Sorry, proceed. Thank you. All right. Okay, so let's take a look at that particular number, and then we say, okay, what is the largest power of 2 that is less than or equal to this number? 256. Okay, 256 is a power of 2. So we say, okay, it has 256 in it. And once we take care of 256, what is the remaining amount? Is it 11? $11.25. Okay. So now we want to take care of the 11 something. What is the largest power of 2 that is less than or equal to 11.25? 8. Okay. 8 is good. And then we have 3.25 left. And now we look at the remaining portion, which is 3.25, and then we ask what is the largest power of 2 that is less than or equal to that? 2, okay. That's 2, and then 1.25 has a 1 plus a 0.25. And fortunately, in this case, 1 is a power of 2, and so is 0.25. It is also a power of 2. 0.25 is 1/4, and 1/4 is 2 to the power of -2. Very good. All right. So now it's time to rewrite all of this stuff as powers of 2. 256 is 2 to the power of what? 8. Okay. And 8 is 2 to the power of
2 to 3.
3. 2 is 2 to the power of what? 1. And 1 is 2 to the power of what?
0.
And then 0.25, as I said, was 2 to the power of what? -2. Okay, let me just realign things a little bit so it's easier to see. So this 2 goes here, this 1 goes here, and then the 0.25 goes here. So everything is kind of aligned now. Okay. What do you think 2 to the power of 8 looks like as a binary number?
1.
Okay, that's good. That's a good starting point. 1 followed by...
7 zeros.
Okay, what is 1 million? How do you write 1 million as a base 10 number? It's 1 followed by 6 zeros. So what do you think this number is? 8 zeros. Okay, it's 1 followed by 8 zeros because the number of zeros on the right hand side indicates the power that you're dealing with. Okay, so this becomes 1 and then followed by 8 zeros. It's a base 2 number. So I'm gonna I will realign things a little bit. So let me just copy and paste this row and just realign things so it's easier to read. Okay, what about the other one? What about 2 to the power of 3? 1 followed by 3 zeros. Okay, 1 0 0 0 in base 2. What about 2 to the power of 1? 1 0 in base 2.
We got 3.
Well,
I
no,
don't know that.
It's right next to it.
I only have those. Yeah, I only have these powers of 2. What about 2 to the power of 0? It's 1 followed by 0 zeros, right? Yeah, so it's just 1 all by itself. What about 2 to the power of -2? Okay, whenever you have question about this, think back with decimal numbers. Okay, what is 0.01? 0.01 is 10 to the power of what? -2. -2. 0.1 is 10 to the power of -1. 0.01 is 10 to the power of -2. And the reason why it's -2 is because it is 2 places to the right hand side of the point. Okay, so now we have 2 to the power of -2. How do we write this using the point? The power is -2, so it's still 0.01. 0.1 is to the power of -1. 0.01 is to the power of -2. 0.001 is to the power of -3. Whatever base you choose to use, but that's how these numbers are represented. Okay, so now we have this kind of awkward form of a number. So next we have to align things a little bit so it's easier to read. So I'm just going to realign things so that it's just easier to look at these things. How's that? Now they're all aligned. Okay, so basically for the first 4 rows, there's an implicit point that I'm using for alignment purposes, and then the last row, which is 0.01, has the explicit point, over there. So regardless of the base, do you think the addition of numbers like these would matter? Nope. Okay, because there's no carry. If there's no carry, what base you're using, would not matter, because you're either having 0 or 1 of one particular power of a number, so there's no carry. So if there's no carry, I can just kind of combine these numbers and just pick out the ones, where there's a 1, and here's base conversion. You're just thinking in terms of using powers of 2s. Okay, how many powers of 2 do we have of this particular power? and so on of this exponent. Is that are you guys doing okay with this? Just at least in terms of the concept in general. Yeah, just think in terms of money, okay? Just think, you have dollar bills of 1, 2, 4, 8, 16, 32, 64, 128, 256, 5, 12, 10, 24, and so on. Okay? And then you're just saying, okay, do I need one of these? Yes. Okay, pick a 1. Do I need one of these? No. Put a 0, put a 0, put a 1, put a 1, and so on. And then whatever pattern you end up with is your binary number. All right? Now, remember earlier I said this is actually supposed to be easier than making figuring out change for the dollar amount. And the reason is simple. Look at the denominations. 0.01 of a dollar is a penny. 0.05 is a nickel. 0.10 is a dime. 0.25 is just a quarter. And then we have $1 bills. I know we have $2 bills, but they're uncommon, so we'll skip to 5, 10, 20, 50. And since I usually don't deal with anything more than 50, we'll just stop there. Okay? But look at the multiplier to take you from one denomination to the next. Okay? This is a 5-fold increase. This is a 2.5. Now we have a 4. Back to 5. Back to 2. And another 2. And then another 2.5. Do you see a pattern here? Nope. There's no particular pattern. Well, not the same one anyway. Okay. Now, if you look at the other money system that I want you to think in, okay? So we have 0.25 as a quarter, 0.5 as a half, 1, whoops, 2, 4, 8, 16, 32, 64. Is there a pattern?
Yes.
There's definitely a pattern. Okay? So that's why if you can deal with this, you already know more than what you need in order to deal with binary numbers. So what you need to do is to kind of tweak the way you think about things, and not really to think about it as powers of a number and bases and stuff like that. Just think that your denominations are kind of weird. Instead of the usual ones, now you have these kind of they're all powers of 2. And once you think in that fashion, the only thing that is a little bit tricky is how to write out numbers changing from 2 to the power of 8 in base 10 to 1 followed by 8 zeros as a base 2 number. That is the only part that is kind of tricky that you cannot take care of just by saying, oh, okay, we have 1, 2, 4, $8 bills. But it's not too bad, because when you look at a binary number like this one, this digit tells you how many $1 bills we have. This one tells you how many $2 bills we have. We don't have any $4 bills. We have 1 $8 bills. None of 16, 32, 64, or $128 bills. And then we have 1 $256. On the other side, we have 0 half dollars. And then we have 1 quarter. Okay? So if you look at it that way, the digits make sense too. Each one is just telling you how many of these things do we have. Are we still doing okay at this point?
Yeah.
Okay? Let's try another example. Let's try something that is maybe a little bit more extreme. We'll just take the whole number this time. This is a base 10 number. And this time I want to convert it into a base 3 number. Instead of a base 2, let's convert it into base 3. Okay. But Ted, you haven't said anything about base 3 numbers. I'm totally baffled. I cannot go forward, at all. Okay. So instead of thinking in that direction and stopping yourself from going forward, think in the other way. With with binary, we think in 1, 2, 4, 8, 16, and so on. With base 3, we think in powers of 3. 1, 3, 9, 27, 81. 81 times 3 is 243. Okay? We think in those terms. Okay? But the method stays the same. It's exactly the same method. Okay, let's take a look here. So what is the largest power of 3 that is less than or equal to 267? We just said it earlier, right? 243, okay? And the remaining portion is 24, I think. Okay. And 24 itself, what is the largest power of 3 that is less than or equal to 24? 9. And how many of 9s do we have in 24? We got 2. Yeah, 2 9s. 2 times 9, and then the remaining portion is 6. Okay, so we'll go ahead and copy the first portion here. With 6, what is the largest power of 2 that is less than or equal to 6? 3. And how many of those do we have? 2. Okay. Okay. And that takes care of everything because the remaining portion is a 0, and we don't have to do this anymore. Okay, so now we look at 243 and say, well, we know this is a power of 3, but which power are we talking about? What is the exponent? Was it 5?
27, 4, 81.
Yeah, it's 5. Yep, good job. So we have one of these. I'm just emphasizing that we have one of those things. And then we have 2 of 3 to the power of 2, right? Because 9 is 3 squared. And then we have 2 of 3 to the power of 1, which is just 3 itself. And that's it. Okay, we don't have any 1s. And then you look at these numbers and go like, okay, I can see that every single one, every single component of the addition of the sum is just a number, a quantity, times a power of 3. So now we are ready to turn these numbers into basic, base 3 numbers, and then we just have to add them up. 1 times 3 to the power of 5 as a base 3 number, what do you think it looks like? 1 followed by 5 zeros. 1, 5 zeros, and then I use parentheses 3 as a indication. This is a base 3 number, and we'll go ahead and line up everything. What about 2 times 3 to the power of 2? The digit specifies how many, and then the number of zeros indicate which exponent we're dealing with. And this time we're dealing with 2 to the power of 3, 3 to the power of 2. That's why we have 2 zeros after the 2. Yes?
But that would never come up in binary because it always increases by a power of 2, so it matters.
That is correct, because that's why binary is so useful, because there's no division involved. It's just a comparison, because you either have it or not have it. There's no such thing as how many do you need. It's always, if you need 1, there's only 1. You cannot have 2. But in other bases, you do have to do the division and find out how many of a particular power of a base do we need. Okay, so that's good. Let's move on to the next one, which is this guy here. It's 2 times 3 to the power of 1. So we still have a 0 because it is still 3 to the power of 1, and that 1 tells me that we need 1 0. So it's 2 0 in base 3. So I'll just make it very clear that we are dealing with base 3 numbers here. And then we'll go ahead and realign things. Oops. There we go. Now they're all aligned. Okay. Now that we have things aligned, the next thing we have to do is to kind of stack them up vertically so that we can align the implicit point like so. And you can see that with each column of the addition, we only have 1 non-zero at the most. which means there's no such thing as carry when we perform the addition. And without any carry, you don't have to worry about which base are we dealing with, because you only have to worry about which base are we dealing with when you have carries. When we don't have carries, it's easy. You just have to say, oh, okay, we have 100220 in this case. So 100220 in base 3 represents 267 as a base 10 number. All right? But you can see how we are just changing the way we think about things. Okay, we're just thinking, how many powers of this base do we have? And you start with the larger powers. Are we doing okay so far with base conversion, or how to look at a number and kind of make it basic? It's like, oh, what is the digit in the number? Well, it just tells you the quantity of a particular power of the base that we choose to use. All right? Now, this is important stuff, okay? This is actually important stuff, not only because mathematically this is kind of interesting, but also because in a computer, everything is represented in base 2. Why do you think inside the computer everything is represented in base 2? Because everything is on/off. Okay, the transistors are either on or off. On the CD-ROM, either you have a hole or it is reflective. When you're dealing with transmission, either there's a voltage present or there's no voltage present. Okay, so everything is either there or not there. And that's why binary numbers work really well, because all you have to do is to say, oh, if the voltage here is 0, I'll use it to represent the value 0. When it is non-zero, I'll use it to represent the value of 1. Okay, so that's why binary numbers are very important in digital computers, because inside the computer, the memory is all organized in binary numbers. Okay, either 1 or 0. When you transmit data, it is also in binary. When you store data, it is also in binary. Are we doing okay so far with the importance of binary numbers? Okay. So now that we understand basic base conversion, we'll go ahead and deal with actual C++ topics. Now, in other type of scenarios, there are other ways to represent numbers. BCD or binary coded decimal. It's kind of like a weird way to represent numbers. It's not very efficient. It takes a lot more storage to represent numbers. But in financial institutions or financial applications like Social Security, your online banks and stuff like that, they have to use BCD because they need to deal with exact numbers. Okay, binary numbers work really well, but for certain applications, they don't work as well. Okay, but since this is a C++ programming class, not a COBOL programming class, by the way, if you know COBOL, you will have no trouble finding work. Yeah, the state will come look for you. They will bang your door. They will come grab you and say, you have to work for us. But I'm already working for that other department. No, you work for us now. Do you guys know why? Yeah, because one, they don't want to change the COBOL programs, to newer programming languages. Okay, because usually when you have a transition like that, it will take years, decades, for the programs to stabilize again. And two, some of the original COBOL programmers have passed away. They're not just retired. You cannot get them back anymore. They're not retirees. They're dead. Okay. Okay. So they have a shortage of COBOL programmers as a result. Okay. And that's why if you learn how to program in COBOL, there's actually a lot of jobs out there, for COBOL programmers. Has anyone seen a COBOL program? No one? Okay, I used to program in COBOL for like a summer or so. It's a summer project, and a COBOL program reads like a novel. It's very verbose. I mean, you spell out everything, including adjectives and. Oh yeah, I mean it just reads out like a story. There's nothing like open curly brace, and the semicolon and stuff like that.
No punctuation?
Huh?
There's no like actual punctuation?
It has
like-
some punctuations, but it reads just like English, with a COBOL program. It takes a lot of typing,
Yeah.
right?
Yeah.
And then you remember COBOL is an old programming language, so some of those programs were not keyed in using a keyboard. Punch cards.
Ooh.
Yeah, it's brutal, with a very verbose programming language like that, and you have to use punch cards. It's extra brutal.
Terrible. That's why
Yep.
it was only a summer.
Yeah, but look it up if you're curious. How what COBOL programs look like. Okay, so getting back to 2014, we are using C and C++. So in C and C++, int, is a type, is an integer type. Okay, and in this class we'll use this type a lot. Okay, integers are a very common type that you use in most programs, in modern programming languages. Okay, so the question is, what is the width of an integer? In other words, when you specify, I need something to store an integer, inside the computer, you can only allocate a fixed number of digits, a fixed number of storage to store a particular integer, which is not consistent with how mathematicians understand integers. If you go to a math class and then you ask your professor and you say, how many digits do I need? Doesn't matter what base, okay? How many digits do I need to store an integer? Your professor would look at you in a very confused way and go like, I don't know, because integers can be infinitely large, right? So potentially, there's no limit of how many digits are required to store an integer. Unfortunately, with a computer, we cannot say, oh, we'll allocate as much storage as needed to store an integer. We have to fix it, right? And that's called the width of an integer. So the width of an integer is usually in base 2. So with modern day processors, it's usually 32-bit, and we are transitioning to 64-bit these days. It has to do with inside the processor, what is quote unquote a natural width of processing. So with a 64-bit processor, which is more common these days than not, that means inside the processor, it can add a 64-bit number to another 64-bit number in one clock cycle. So that's why it's called a natural width of the processor. Okay. Are there any questions at this point? Okay. If there are no questions, we're going to move on. So assuming that W is representing the width of an integer, and that is basically measuring the number of bits that we use to store an integer. And a bit, BIT, represents binary digit. The B comes from binary, and then the IT comes from digit. So a bit is just one single digit of a binary number. So knowing that there are W bits in a number, the most negative value you can represent is -2 to the power of W minus 1, and then the most positive value you can represent is 2 to the power of 2 to the power of W minus 1, and then that whole power sub minus 1. The minus 1 is there because 0 is also taking up one spot. So that's why we can only go up to that power of 2 minus 1. Any questions about this part? And that's why you see on the whiteboard here, I have this calculation, which is based on 32-bit. If we allocate 32 binary digits to store an integer, what is the most negative quantity that we can represent? So we have 2 to the power of 32 minus 1, which is 31, and then the negation is on the outside. And the way we do the estimation is we look at 1,000 in base 10 and say, well, that's pretty close to 1024, and 1024 turns out to be exactly 2 to the power of 10. So that's why we look at 2 to the power of 31, and then we say, can we break it up into components involving 2 to the power of 10? And the answer is yes, because 31 is 10 plus 10 plus 10 plus 1. But 2 to the power of 10 is about 1,000. 2 to the power of 10 is 1,000. And then 2 to the power of 10 is 1,000. Okay, so approximately using the approximation symbol, we have 1,000 times 1,000 times 1,000, and then this 2 is just a 2 out here. So that gives me about 2 billion. So negative 2 billion is about as negative as it goes when you use 32-bit to represent an integer. All right, which is not a very large number. It's not enough to represent our national deficit. It's off by how many zeros? Just a few. Like 3. Yeah. If you think about it, that's a pretty big number.
Do the negatives cancel each other out in binary? So like, would you be able to get -4, or how does that work?
Say again?
If you're going 2 to the power of 2 is -4, but that would be -2 times -2 is +4. So how do you get around that?
Well, I'm not going to use -2 as a base, so that would not be a problem.
They said, how would you represent -4?
Yeah.
But
How do we represent -4?
he's not going to get there, but there's like, it's a sign that, so you'll...
Yeah, it's a little bit beyond the scope of this class, but what we do is we use 2's complement to represent negation. So it uses the same bits, zeros and ones. It doesn't really have a particular thing just for the sign of a number. So to represent negative numbers, we only use zeros and ones, just like positive numbers. So the way we say that, oh, this number is representing a negative quantity is to make use of a convention called 2's complement. In the next class, CISP 310, we will learn about 2's complement in that class. All right. So are we okay with base conversion for one thing? And then after that, the width of integers. So that's all doing okay so far? Okay. So now we go back to logical versus bitwise operators. When we deal with logical operators, okay, this is the logical operator AND, also known as conjunction. And this is what we call a truth table. With a truth table, I'm defining the input as X and another input as Y. Now these two are independent inputs. In other words, when X is 0, Y can be 0 or non-zero. When X is non-zero, Y can be 0 or non-zero. There's no correlation between the two variables X and Y. And that's why we end up with 4 possible combinations, because each one has 2 possible states. When we combine these two, we have 2 times 2, which is 4 possible input configurations. I know in your previous class you probably know this as false, and you know this as true. But in C and C++ programming, there's no true Boolean values. Okay, we really only have integers to represent Boolean values. So that's why we can only say that is it 0 or is it non-zero. 0 is the same as false, and a non-zero is the same as true. So once you do the conversion between 0 and non-zero into false and true, then it makes sense, right? Because now we have false and false is false. False and true is false. And then we have true and false being false. And then the only time you have a true as a result is when you have true and true is true. Okay, so it's basically the same kind of table, Boolean table for conjunction, except in this case we have zeros versus non-zeros instead of true and false. This one is for disjunction. So when you look at disjunction, it's kind of like the flip side of conjunction. So when you look at disjunction, the only time you can end up with a 0 is when both sides of disjunctions are zeros. And then for all other cases, the result of a disjunction is non-zero or true. Are we still doing okay so far at this point? Why do I say non-zero? Why can't I just say 1? 0 and 1 is so much easier to understand. Well, that's because this is the C++ language definition. Okay, the C++ language definition only states that when the result of a conjunction is true, it will return a non-zero value. It does not say which non-zero value. So when you have 32-bit as an integer, then you have 2 to the power of 32 minus 1 choices for non-zero values. And any one of those can be considered as true. So this brings us to negation. Logical NOT, which is negation, is really simple because when the input is false, not false is true. When the input is true, not true is false. Now, this is a very common issue, and I would not be surprised if multiple people in this class will repeat this mistake a few times. Okay, it takes a few times, before things get soaked in and understood. It is 2 ampersand here and 2 vertical bars here. If you use a single one, it becomes a bitwise operation, which is about the same thing, but not exactly the same thing. Okay, well, I'll explain what a bitwise operation is as opposed to what a logical operation is. But before we move on, I have just one example down here, just so that you can look at this and try to figure it out. What is the result of this particular expression? We have 5 logical and in parentheses 3 is less than 4. What is the output? What is the value of this expression?
Or some non-zero number.
Non-zero. Okay, that is correct. Okay, non-zero is the proper answer. True is okay, but you have to kind of translate that back into C++ terms, which is non-zero. Why is it not 5? It can be 5, but it's not limited to 5 because it can be any non-zero values. So 5 and 3 is less than 4 can give you a value of -14, which has nothing to do with these numbers. Are we doing okay so far with the concept of 0 versus non-zero? Okay. So with that out of the way, we're now moving on to bitwise operators. To understand bitwise operators, this is the main reason why we had to deal with base conversion before. Because bitwise operations means we apply the same operation to each bit of an integer. Okay, so I'll give you one example. Okay, let's look at this one truth table here. If you look at this truth table, bitwise AND, it looks almost identical to the logical AND truth table, except certain things, very subtle things, are slightly different. One, the name. Okay, bitwise AND versus logical AND. Okay, that's just a name. But the other thing that are different is instead of referring to the entire integer of x, now I'm only referring to a particular bit of that integer. Instead of referring to the other integer as y, the entire thing, now I'm only referring to one single bit of y. Instead of referring to the entire output, I'm only referring to one bit of the output. Okay? And instead of using non-zeros, this time I'm using actually 1, zeros and ones. And that's because if you look at one single bit of an integer, it's a binary digit. As a result, it can only be a 0 or a 1. And that's why this time it's okay to use 0 or 1 because that really are the only choices for a particular digit in a binary number. All right, but let's see how we can apply this table. I'm going to leave the table here, and then I'll give you an example of how to use that table for bitwise AND operation. So I will start with decimal numbers, and then go through the whole process of converting it into base 2, perform the bitwise AND, and then convert it back into base 10. All right? So you guys can choose numbers, okay? I don't want to choose a particular number. So pick any number from 0 to, say, 200. I don't care.
79.
Go ahead.
79.
79. Somebody pick 79, and somebody else can pick something else. 150? Okay, let's pick 150. And I have no idea what the result is, but I'm going to go through the whole process to show you, how to do the conversion and then how to perform the bitwise AND and get to the result. Okay? So I cannot look at the base 10 representation and perform the actual operation. Maybe some people can, but I cannot. Okay? There's actually a trick to do that too, but I'm not going to go there. Okay, so the first thing is we can look at these as binary numbers. 79 is a binary number. Okay, so how quickly can we do this conversion? Okay, 79, so I'm going to separate these into two kind of columns here. 79 has 164, right? So 164 will give me 6 zeros, because 64 is 2 to the power of 6. So the 64 would have left 15. And 15 is an easy one because, you know, just by memory, 15 is 1111 in base 2.
Yeah.
Because it's just 1 less than a power of 2, which is 16. So that's why it is 1111, you know, 1 plus 2 plus 4 plus 8 is 16. Is that right?
Yeah, 4 ones.
1 plus 2 is 3. 3 plus 4, I missed the 4. Yeah, 3 plus 4 is 7. 4 plus 8 is 15. Okay, so I'm just going to shortcut it a little bit here. And so 79 in base 2 has this representation. So let's go ahead and emphasize this is a base 2 number. And now we can move on to 150. 150 has a 128. Yep.
That'd be 4 ones?
Yeah.
Oh, you're right. 4 ones. Sorry. Okay, let's look at 150. 150 has a 128. 128 is a power of 2. It is 2 to the power of 7. So we have 1 followed by 7 zeros. And once we take out 128, we have
22.
what, 22 left?
Yeah,
And 22 has a 16 in it. And the 16 is 2 to the power of 4. So that is 1 here. So 22 minus
8.
16 is it 8?
Yeah.
Okay. So 8 is just here. So the final result is this number. Okay, now it's time for sanity check. Okay. Sanity check means, you know, we're going to look at these numbers and convert it back into base 10 to make sure that we end up with the same base 10 numbers. Okay.
You have 279.
Say again?
I think you have one more place value than you should on 79.
Oh, the leading zeros are easy. You can put as many leading zeros
No.
as.
I know.
No, I mean the one should start on the 64.
Yeah, 64 has 6 zeros. That's correct. 64
Oh, okay.
is 2 to the power of 6, and that's why we
I
have
missed
1 followed by.
space.
Okay, that's okay. No problem. Okay, but now it's time for, you know, sanity check. This one is easiest, you know, for sanity check because it's 64 plus 15. 64 plus 15 is 79. Okay, so that one is easy. The other one is, well, not so easy, but there's a cross-check way. We look at this number here and then we say, what is the base 10 representation of 10011, which is 3 times 6, 3 plus 16, because 11 is 3, and the 1 followed by 4 zeros is 16. So 16 plus 3 is 19. Okay, so we know that there's a 19 in it. Oh, I think this is not going to work.
That's what I said. That one's wrong.
That one is wrong. It has to be wrong.
16 plus 6.
Yeah. Right.
Yeah.
16 plus 6, so
So 2 to a second, and then a 1.
we need 2 ones here. Quick sanity check, you know, reviews. It's not right. Okay, let's look at this number and see if it makes sense, right? So now we look at this part here, and then we ask, is that 75? Because that 0 here, this 0 on the right-hand side, basically means times 2. Okay? So we look at the other part of this number, and we ask, is that 75? We have 64. This is 8. 64 plus 8 is 72. 72 plus 2 is 74. 74 plus 1 is 75. So the highlighted portion is in fact 75. And then the 0 to its right-hand side is just saying, oh, multiply that by the base. Well, which base are we using here? Base 2, so it's times 2. so that way we get 150 back. So the sanity check works out. Okay. Okay. Now that we have these two numbers represented in base 2, it is time to stack them up vertically to perform the bitwise AND operation. So the first number is 79, which is 1001111 in base 2, and then the second number is 10010110, and because one is a little bit shorter than the other one, we can just add zeros, leading zeros, to line them up and so that they have the same width. Okay? Because leading zeros do not change the value of a number. It just makes it nicer to look at. All right. What is 0 and 1? Well, you just look up the table. 0 and 1 is 0. 1 and 0. 1 and 0 is 0. 0 and 0. 0 and 0 is 0. And then we have 0 and 1 being 0 again. 1 and 0 being 0 again. 1 and 1 being 1, because we have 1 and 1 is 1. And then the same thing here, and then 1 and 0 being a 0 again. That's a base 2 number. And so that means, this thing ends up with 110 as a base 2 number, which is 6 in base 10. Kind of awkward. But that's how it works out.
What does that mean? What does that 6 mean?
Whatever you want.
The 6 means, well, that's how we compute the answer, okay? But why do we need to do all these bitwise operations? I mean, who in the world, will need to perform calculations like this, right? Addition we can understand, multiplication we can understand, even logical operation we can understand. But bitwise operations, something like this, why do we need something like that?
You get your data.
Well, the most immediate application of something like this is for input-output operation inside a computer. So I'll just kind of go a little bit into how your computer performs input-output. This is a little bit out of the scope, but I do want to explain it just so that you have a context to understand why these are important stuff to understand. Okay, so inside your computer are what we call I/O registers, or input-output registers. A typical input-output register has only about 8 bits. Okay, they're not really big. But the problem with I/O registers is each bit, each binary digit, is used to control something different. Okay, think about your hard drive controller. Okay, with a hard drive controller, one of these bits may mean, is this a cached operation? Should I make use of the hard drive cache, or should I ignore the cache and just write the content onto the hard drive? Okay, so this one bit here, which can be a 0 or 1, is basically to say, should I use the cache on the hard drive or not? Okay, another bit here may identify, should I optimize the movement of the head? In other words, if I have a queue, okay, a line, basically a collection of pending operations, instead of having your hard drive to go, in the same order as the requests come in, if you can reorder the operation, so then it can actually go a lot faster, because you just have to go in one direction and finish all the operations instead of having your disk head to seek all over the place. Is that okay? So this is just an example. So this one is basically saying, travel, disk head travel optimization. Should I turn it on or should I turn it off? There may be occasions where you want to turn this off, okay, and make sure that each operation is performed in the same order as it arrives on the hard drive controller. Other bits may have other type of configurations. Maybe you have 2 bits, to specify one of the options, like how fast is the DMA, direct memory access. Okay, that basically determines how quickly your computer can dump information onto your hard drive. There may be occasions you want to make it slower and not go for the highest speed. So these 2 bits combined, to 0, 0, 0, 1, 1, 0, and 1, 1, that gives you a choice of 4 possible speeds for your DMA controller. In other words, you look at these 8 bits, you're not looking at the 8 bit as a number. You never interpret these as a number from 0 to 255, because each individual one controls controls a different attribute of your hard drive controller. So how do you turn one on without affecting the other one? How do you turn off one without affecting the other ones? Bitwise operations. Okay, with bitwise operations, you can say I only want to turn off this one bit, but without affecting any of the other bits. Yep.
That makes a lot of sense when you're looking at the result, base 2 result. Is there any actual value to the number 6 that we come up with in base 10?
Say that again?
So the result we have tells us whether these two things line up, whether it's true to do something. But when you convert that back to base 10 like we did, is there any reason to do that? It seems kind of...
It's only when you print it out, it will display as a 6. You are absolutely right. Okay, so your point is well taken, which is basically this number here, or the quantity as 6, is not really useful most of the time. Simply because it is used to control, it's going to be spilled out into an I/O register, and it's going to be used to control the hard drive controller. It's not for somebody to see. It's really just for the controller to do its proper thing. Absolutely. This is why bitwise operations are important. It's for low-level type of programming. Now, if you're dealing with Java programming, I would say most of the time, you won't encounter bitwise operations, because Java as a programming language is not suitable for low-level programming. You can do some, but usually it's not intended for low-level programming. C and C++, they are used to write the majority of operating systems. If you look at the Linux operating system, it's about 90-something% in C, and then the remaining portion in assembly language. But this is a C++ class. I don't need to know anything about C. Well, C++ is a superset of C. So that means, in this class, not only do you need to know about C concepts, but also C++ concepts, because C++ is a superset. It includes the C standard itself. All right. Are there any questions about bitwise operations up to this point? Now, let's look at one. I'm going to handpick one particular example just to illustrate the importance of differentiating between logical AND as opposed to bitwise AND. Okay, so I'll give you this example first. So let's say the 18. Okay, 18 on one side, and then we have on the other side. Let's pick 131. Okay. 18 as a base 2 number. It's pretty easy. It's 1 1 0 0 0 1 and then 0 0 1 0. And the reason the way I did this conversion is converting into base 16 first and then back into base 2. But you can also see how this works because it has 116 and 1 2. How many 1s do we have? None. How many 2s do we have? 1. How many 4s do we have? None. How many 8s do we have? None. How many 16s do we have? 1. And so on. So this is 16 plus 2, which is 18. The other number is not too hard either. Okay, 131 has 128, and then a 3, which is basically just 1 1 at the end. Oh, this is not going to work out. Change it a little bit here. Let's make it 129. I have to doctor these numbers because I want to show you one particular effect. All right, so that's 1 plus 128, which is 129. Okay, so when you look at the bitwise AND of these two numbers, 0001, 0010, bitwise AND 1000, 0001, I don't have to look up the table to tell you that it's going to be zeros. Okay, because you cannot find one column to have 2 1s, and so that's why they're all going to be zeros. Okay, no big deal. That's a 0. what about the logical operation? What about 18 on one side, and then you have 129, but this time we are using the logical AND operation. We have non-zero on one side, we have non-zero on the other side. So what is the result of this logical AND operation? Non-zero, exactly. We don't know whether it's 18 or 129 or 1 or -1. We just know it is non-zero. Okay. Now is a problem, right? Because depending on the implementation of the compiler, it can give you numbers after comparison that always will work even with a bitwise AND operation. On the other hand, it can also give you values after a comparison that will end up with a 0 if you use the bitwise AND, but if you use logical AND, it will give you non-zero. Okay, the bottom line, if you're not quite getting what I just said, the bottom line is if you use a single ampersand mistakenly when double ampersand is supposed to be used, your program may not show any problems. Depending on what compiler you're using, what processor you're targeting, and a few other things. So your program, for the most part, may work perfectly even though it is slightly incorrect. But the moment you take the same program and you recompile it using a different compiler for a different platform, or just change one of many things that can affect it, the program just falls apart and not work anymore. That is one of the worst type of problems, because if a problem is consistent across all the platforms, across all the targets and whatnot, it's fairly easy to debug. This is not. The other thing that is really nasty is because this looks just like that, except it's double. Okay? If C requires you to spell it out, okay, one is just AND and the other one is spelled out as bitwise AND, then it will stand out. Okay, visually you can say, oh, okay, that's not what I want. Okay, but this really does not stand out. Okay, I have seen a lot of people, people who have been programming for years and still make mistakes like that. Okay, double equal is another evil one. Okay, one is comparison, the other one is assignment. And interestingly, they can go to the same places. And syntactically, most of the time, it is okay. So you got to watch out for these things. All right, so now that we know what is bitwise AND, bitwise OR is about the same. The only thing that is different is 0 or 1 is a 1, 1 or 0 is a 1, 1 or 1 is a 1, and the only time it has a 0 is 0 or 0 is a 0. Bitwise not. Not 0 is a 1, not 1 is a 0. So you're just flipping all the bits, okay? If it's a 0, it becomes a 1. If it's a 1, it becomes a 0. And then we have one last one that is not, there's no equivalent logical operation, which we call bitwise exclusive OR. Exclusive OR is represented by the caret symbol here, which on the keyboard is Shift 6. And the only difference between this one and logical OR is the last row. One exclusive OR 1 is a 0, as opposed to 1 OR 1 is a 1.
What's an instance where you would use that?
To use exclusive OR?
Yeah.
One
It
of
says something like a kind of OR, or
Well, exclusive OR has an interesting property of it's easy to recover. Okay, let's say we have two numbers. Okay. Okay, let's say that C is computed as A exclusive OR B. Okay, so C is the result of A exclusive or B. Then we can actually get B back because it has a relationship like this.
oh, okay.
So that's why exclusive OR is kind of an important thing for parity check. Some checksums make use of exclusive OR. Checksum is basically a little bit of a bit pattern that you attach to a file when you transmit it, and so it's kind of like a verification kind of thing. So let's say you have a 4 kilobyte file, okay, and you transmit it, and then you transmit what we call a checksum, which is kind of like a signature. A checksum can be 16-bit, can be 32-bit, but it's usually not a very long number. And it's it can be computed using exclusive OR and a few other mechanisms. It's for checksum purposes. In other words, the recipient of the file can independently compute the checksum and compare the computed checksum with the transmitted checksum. If they're not the same, that means there's a problem with the transmission process. And exclusive OR is used a lot with checksums, in the past. But these days, we don't use it too often. It's not the same anymore. And once again, when do we end this class? Is it 30 or 35?
30.
30? All right. So we're done here.
The cobalt.
Oh, yeah. Forgot about that. All right. So it's all done. We'll go ahead and install it. So you can go if you don't need to watch this part. It won't take long. Okay, when you install, you have to make sure that main GW compiler suite is a part of it. Okay, if you don't see that as an option, you probably downloaded the wrong installer.
Well, I saw that too. It had it.
Okay, well, let's go ahead and install it, and we'll run a quick sample program. That's actually not bad, considering this is Windows 7 in an emulator.
Going back to my fault.
But these computers, this one is actually really fast.
So I thought I gave you my prereq slip, but if I didn't, because I got
What's your
dropped.
last name?
Pollock?
Okay.
You want me to get you a new one? Because I'm fairly sure I gave it to you.
Yeah, I think so. I think I remember you, because I see you, but when I look at the name, I don't remember whose name it is.
In this class.
So you can go get a petition form. Unfortunately, you need a petition form to add back to the class.
Yeah.
But I will sign it, so that's not the issue.
Okay.
Yeah. Sorry about that.
No worries.
Right.
I think I had the same problem he did. I got dropped from the class.
Okay.
So I had to notice it. I even got a phone call that said it was approved.
Okay. What's your last name?
Roberts.
Because I don't see, sometimes they send an email, when they approve, and I see the student's name, with approval, and I guess it depends on who processing. I never got one, from yours. Did you give a slip of paper to me?
No, they never gave me anything. They just gave me a phone call saying you were approved, and that was it.
So what happened was when I started it up, like the message where the compiler was missing the file.
Hello.
You missed it.
We're
That
having
was the
class
part right there.
at 3, so I'm sorry.
Oh, okay, sorry.
No, you're fine.
So you just do console.
Yeah, he just did it. Because that whatever
Yeah,
version
so
he used
that
the
works.
last time was a different version of
Okay.
this, and there were 2 other things he had to click, but that time around he just clicked the one thing on the first
Okay.
page.